So I would like to welcome Guram Bezhanishvili from New Mexico State University, who will speak on modal operators on rings of continuous functions. So between modal logic and functional analysis.
Yeah, somewhere in between.
Yeah, a very interesting topic. Welcome and please begin.
Thank you, Lev. It's a pleasure to be here again. During the summer, I gave a talk which was slightly different topic, and then there were too many good questions. So some of them we're still trying to solve. So, if I get the similar type of questions, then I think I'll be busy for the next year. But the topic here is rather different. So the previous topic was connecting set theoretic axioms with topological completeness in modal logic. And here what I'll be talking about is connection of modal logic, algebra, and analysis. You probably see on your screen, at the top of the screen that I'm sharing, there are different sections of the talk that I'll be talking about. I have probably more slides that I can cover. So my goal is to tell you the modern outlook on Jonsson-Tarski duality, which can be thought of as the basis of modal logic, or rather how I think about it. And then I'll tell you this section 3 is what's known as Gelfan duality. This is the branch of mathematics that connects algebra, topology, and functional analysis. And so my goal is to basically give you a crash course in these two areas. And then everything that happens after that is going to be a bonus. And so if I run out of time, Lev, please stop me and I'll be happy. If I achieve the goal to advertise Gelfan Duality well enough, then that's what I want to do. Everything else is going to be a bonus. Okay. So the way that I want to think about Jonsson-Tarski duality is a kind of extension of stone duality. And stone duality is a celebrated duality from 1930s. It establishes that the category of Boolean algebras is dually equivalent to the category of what we now call stone spaces. These are special compact Hausdorff spaces that have a basis of clopens sets. And the important connection from how to go from stone duality to this Jonsson-Tarski duality is basically to study modal operators on Boolean algebras or operations on Boolean algebras by means of additional structure on stone spaces. And one way to think about this additional structure on stone spaces is the so-called continuous relations. Continuous relations generalize continuous functions. These are what I displayed on the screen are the two conditions that continuous relations need to satisfy. Take an arbitrary binary relation, then you look at the points. R of x is all the points that x can see. That should be a closed set. And then the R inverse image of each clopen needs to be clopen. You see that this gives direct generalization of what continuous functions are, because if your relation is a function, then the R image becomes simply a point which is always closed, and then the second condition is simply this continuity condition in the setting of stone spaces. This generalization is more superficial to give deeper understanding of what is the connection between why these functions, why these relations are called continuous relations is through this famous construction of Vietoris that goes back to 1920s. Vietoris space is out of each compact Hausdorff space, you can form Vietoris space by working with closed sets of your space. And then you define this topology, and it's not an accident I'm using this language of modal logic. I'm using box and diamond for these basic elements because they indeed behave like box and diamond. And the topology that I'm defining here, this is called the hit or miss topology or Vietoris topology. There are several names for it. So the basic idea is that you look at all, you can, your basis is enumerated by the open sets of your original space X. And what you're interested in in those closed sets that either hit your open set or are completely contained in the open set. And these are the basic elements, the sub-basic elements that generate the topology of the Vietoris space. And what happens is that this is this famous result that goes back to Vietoris, but then as it often happens, you know, Vietoris' paper was ahead of time, and it was kind of forgotten and then remembered again in 1940s and 1950s. So an important paper from 1950s was a paper by Michael, who actually provided this more modern account of Vietoris spaces. And then now these are called hyperspaces. There's an entire direction in mathematics that studies these hyperspaces and has applications to domain theory and other branches of science. Why am I mentioning all of this, right? The reason I'm mentioning all of this is because this understanding of continuous relations gonna happen through this Vietoris space. Now, let's go back to our stone spaces, and now let's think about the connection between these continuous relations and continuous functions into the Vietoris space. If you have a continuous relation R, then we can always define a function into the Vietoris space by simply saying that I'm going to send a point into its R image. And that's exactly why I need my R image to be closed, because I need my function into the Vietoris space to be well defined. And then I need it not only to be well defined, this is this first condition that R of X of each point is closed, but then I also need this raw map to be continuous, and continuity follows from the second condition that says that R inverse image of each clopen set is going to be clopen. And so that shows us that continuous relations give functions into the Vietoris space, and conversely, if you have a function into the Vietoris space, then what you can do is that you can define a relation by saying that X is R related to Y if Y happens to belong to this R image, or this raw image of X is going to be a subset, a closed subset. And now we define this relation R by saying that this closed subset is exactly all the points that, that X sees with this new relation R. And this provides a one-to-one correspondence between continuous relations and continuous functions into the Vietoris space. And so we get this endofunctor, we get this functor, Vietoris functor that works on stone spaces. So on the one hand, you have this Vietoris functor on the stone spaces. And on the other hand, now you want to lift your stone duality to define a functor on Boolean algebras. And this is a key consideration that goes back to, again, 70s and 80s, that this is how this functor can be built. And this is exactly the beginning of modal logic, because this functor that is dual to Vietoris space happens to be nothing more but the free construction that allows you to build a free Boolean algebra over a semilattice by first forgetting the structure of the semilattice and then remembering. So you take a semilattice, forget that it's a semilattice, think about it as a set, then take the free Boolean algebra over it, but then remember that you actually had a semilattice. And remembering that you actually had a semilattice is exactly this part that says here that this box has to commute over binary meets, and box of 1 has to be 1. And this is this functor that provides the algebraic counterpart of the Vietoris functor. And then we obtain this, this theorem that that stone duality between Boolean algebras and stone spaces leads to duality of the corresponding functors. And on the topology side, you have this functor V, the Vietoris functor. And on the algebra side, you get your functor H, which is this, this free functor, that this endofunctor that I just described to you. Historically, this was already anticipated by Essakya back in 1970s. And then I think that then Abramsky was the next important contribution in this line of research, who actually made some of the ideas of Essakya explicit without knowing Essakya's work. And then Ghilardi, without knowing Abramsky's work, rediscovered this, this H functor. And then in early 2000s, Venema, Kupke, Kurz, and Venema actually provided this, this picture, this diagram that I drew down there. This was actually explicitly stated in this paper by Kupke, Kurz, and Venema. And if you heard about this direction in modal logic called coalgebraic logic, then this is exactly what this coalgebraic logic studies. It studies these endofunctors and the correspondence between these endofunctors. Now, how does this relate to Jonsson-Tarski duality? This is just a different way to think about Jonsson-Tarski duality, because remember that Jonsson-Tarski duality on the topology, on the frame side, has the so-called descriptive frames. These are Kripke frames that are enriched with topology. And all that a descriptive frame is, it's really a stone space equipped with a continuous relation. On the other hand, modal algebras are Boolean algebras with this binary, with this unary modality that preserves finite meets, or you can of course work with diamond if you prefer, they are interdefinable. Now here's the key fact that this modality is entirely determined by this free construction that I described, that basically the behavior of box is governed by this endofunctor H that I talked about. And it uniquely determines the behavior of box, because all you need to do is to take your Boolean algebra, then forget that it's a Boolean algebra, only remember that your box from B to B preserves only the semi-lattice structure, and then build your free construction. And this free construction then will give you this alpha homomorphism, and this alpha homomorphism will uniquely determine the box. And now putting these two together gives you that this category of modal algebras is dually equivalent to the category of descriptive frames. And this is the essence of the Jonsson-Tarski duality. And one thing that I want to say is that, as it always happens in mathematics, you know, the names are not really representative of the actual contributions. So I don't know who started to call this Jonsson-Tarski duality. Some people here probably know this better, but this is what's kind of an accepted name now, that this is Jonsson-Tarski duality, but they didn't really have this duality, right? So what they had back in 1951 was that they had this relational representation of modalities, and they provided this study of Boolean algebras with operators from the point of view of relations on the corresponding relations on sets. The actual full duality was established later. I think that I'm mentioning these three names because I think that Halmos was the first who provided topological duality between something that resembles modal algebras and descriptive frames. That was in 1950s, late 1950s. And then it was the work of Essakya and Goldblatt in 1970s that actually made this theorem that we call Jonsson-Tarski duality what it is now, right? So this is this crash course in Jonsson-Tarski duality, right?
May I ask a question?
Yes.
Does it extend to more than unary operations, binary operations, ternary, and so on?
Yes, very good question. So this is something that Jonsson and Tarski had. They actually had arbitrary operations. And so what's going to happen is that on the topology side, you're going to have, depending on if you have an n-ary function on the Boolean algebra, then on the topology side, you will get n plus 1-ary relation. And so then you have to define carefully what it means that this n+1 relation is continuous. But you can do that, and then this Jonsson-Tarski duality works in the multi-modal language setting. Yes, so this is a good question. So indeed, I'm only doing unary here in this talk, but you can handle a multi setting. Questions are welcome, by the way. So if something is not clear, or if you have a comment or suggestion, please feel free to stop me. So now comes what I really wanted to talk about, right? That what's going on with stone spaces is that we have this very special basis of clopens sets, and then this basis makes the stone duality work. But as soon as you go to a more general class of spaces, and this is the class of spaces that mathematicians care more about than just stone spaces, then the situation becomes more complicated, because take the 0-1 interval, for example, the unit interval, that you have no clopens whatsoever, right? And so then, of course, the stone's machinery has to be changed, right? And here's one way to think about it, that think of clopens. You can think of any set, you can replace any set with characteristic function of the set. If the set happens to be clopens, this characteristic function in general won't be continuous. In fact, it is continuous if and only if your set is clopen. And so you can replace clopens by continuous characteristic functions. So then you can think of stone spaces as special spaces in the following sense, that you have enough continuous characteristic functions. And now you don't have enough continuous characteristic functions. So what do? Well, you work with all continuous functions, right? It's very natural to do that, right? And then if you do that, then instead of working with clopens, you're starting to work with this ring of all continuous functions. And I'm making them real values. So my target is always real lines. I'll talk about what happens when the target is complex numbers later on. So then clopens you can identify with a very special subring of this ring of all continuous functions. These are exactly idempotents. An element in a ring is an idempotent if you square it and you get your element back, right? This is the approach taken in, and the history goes even before, but the earliest I want to go to is this paper by Gelfand and Kolmogorov of 1939, when they started to characterize topological compact spaces by means of rings of continuous functions in them. And then Stone actually had similar ideas independently in 1940, in early 40s. And then later on, this famous line of research of Kaplansky also provided some interesting results in these directions. The story doesn't end here, but I didn't put all the references here, right? So the key here is to study the structure of C of X. And the question is what structure we should put on C of X. So if you concentrate only on idempotents, then the structure that you're putting is just the structure of Boolean algebras or Boolean rings. Now, what structure should we put on C of X? Well, one thing is that we clearly have an obvious ring structure. This is how our grandfathers studied this structure. There's addition, component-wise addition and multiplication. But here's a key observation that this structure, just ring structure, is not enough. The best we can do here is something that's known as Gelfand ring. Gelfand rings are the rings in which that are kind of close to C of X, but they are not fully C of X in general. So what happens in Gelfand, if you think about C of X, what happens is this, that if your function, draw a function on R squared, right? So then your function, if it's away from 0, then you can invert the function. So there are many functions that are invertible. And so this notion of Gelfand ring basically tells you that you have many elements that are invertible. And if you only stay with ring structure, then what happens is that you can prove some representation theorems. You can prove that all these Gelfand rings can be represented, admit Schiff representation. But what happens is that in each stock, CX is special. CX's Schiff representation is special in that in every stock, you have entire real numbers. And here you will not have entire real numbers. Your stocks will change, and you will have this continuous Schiff of this continuously changing stocks. And that's just not what we want. We want entire C of X. And so just the ring structure is not enough. And now the question becomes, what additional structure we need to put on it, right? This is what this part 2 of this talk is going to be about, right? And then the addition, there's a number. One thing that happens, for example, is that you can always multiply by the real numbers, right? So you have the so-called R action, right? And so what that means is that on top of your ring structure, you can also have the algebra structure, right? But what is especially interesting for people who work in lattice theory is that there's a very natural lattice order on C of X. And what is this lattice order? This lattice order is also component-wise, because on real numbers, you have an obvious less than or equal to order, and you can leave that to C of X. And then what happens is that this order will behave well with addition and with multiplication, meaning that if you pick two functions which are positive and you multiply them, that'll stay positive. And if you take two functions, one being underneath another, and you add another function, so then this adding this function will translate this less than or equal to relation very well. And so the additional structure that you can put on this C of X is this lattice ordered structure, which works well with your ring structure. And these in the literature are called L rings. So now we're going to the direction of order algebra. This is what order algebra studies. It studies lattice ordered rings, right? Or lattice ordered groups even. So all these names like L groups and L rings and F rings, this is from this branch of algebra called ordered algebra. But so far, nothing about analysis, right? Well, before that, let me also mention that we not only have lattice ordered ring, but we have a lattice ordered algebra, because remember, this R action also preserves the order. And so really what we have is not just an L ring, but an L algebra. And now here come two very important properties that these L algebras have. These are very specific of C of X. This is the so-called boundedness, which comes from compactness. If you have a compact space, then and you take continuous image of compact space, what you get is again compact. And compact on the real number simply means that you are bounded. And so you are gonna have every function is going to be bounded, which means that you can always bound the end, the values by some natural number. So you can find some large enough natural number such that every value of f is going to be between minus n and n. And another important feature that these rings have, this is going now back to the study of infinitesimals, right? That real numbers don't have any infinitesimals. In the language of algebra, that means that they are Archimedean. That means that whatever you take all functions into an Archimedean ring, then this big ring C of X is going to stay Archimedean, right? And so these are the two properties that play an important role for what's coming next, right? So we will have these L algebras, and that's where this name BAL comes from. So this BAL is the category that I'll be working in. So I have rings that have order on them, and then this order and the ring structure relate to each other by these two conditions that were bounded and Archimedean. Right? So so far, no functional analysis, right? But now functional analysis starts to enter the picture, because in addition to the algebra and order structure, we also have a uniform norm on C of X. And this uniform norm is defined this way. You take the range of your function, and then you take the positive part of that, And now you can take the soup of it. And why can you take the soup of it? Why does the soup exist? Because we're compact and so we're bounded. And so this soup exists and so our norm is well defined. And so with respect to this norm, we can talk about uniform convergence, that each Cauchy sequence convergence. And so we have this uniform completeness. And now we're finally getting to all the structure that we have on C of X. And now we're heading towards.
Sorry. Perhaps X should not be on the left side of the equality.
Which
Norm
equality?
of F, just norm of F.
Yeah, but oh yeah, there's time.
Yeah, it does depend on X. Yes,
Yeah,
sure.
so there should be no X. Yeah.
Yep.
Mm-hmm.
Yeah. And so we have the structure on C of X is on the one hand algebraic. On the other hand, and so these are R algebras. On the other hand, it's order theoretic. And then finally, we also have this norm, right? And so this is the structure that we will be working with, right? So these are our two main categories that we'll be working with. So the category of bounded Archimedean L algebras and its subcategory consisting of these uniformly complete objects, right? These are the categories that that were part of my life for the last probably 10 years, you know. So now there's an obvious functor from compact Hausdorff. This was the whole idea of talking about BAL and U-BAL is exactly through this functor of associating with each compact Hausdorff space this ring of all continuous functions, right? And so all this that I told you until this moment is motivation why this C is actually a well-defined functor. Right? So now we're getting to Gelfan duality. Now the question is, how do you go back, right? So now you have this purely algebraic or algebraic order theoretic description of these categories. And the basic idea is that these are the categories that in which all these rings of continuous functions live. And the question is that how can you recover your compact Hausdorff space from these special algebraic structures? And this is done through what's known as the construction, this Yosida space construction, which is generalization of what we do with stone duality. So what do we do in stone duality? You take a Boolean algebra, you take all ultrafilters, and that's the stone space of your Boolean algebra. Or instead of ultrafilters, you can work with maximal ideals. And this is the direction I want to take. So I want to work with maximal ideals, but maximal ideals in this new sense, right? Yosida, by the way, he was a representative of this famous Japanese school of functional analysis alongside with Kakutani. So the main names of this school in the 30s and 40s were Kakutani, Nakano, and Yosida, right? And so Yosida, it's this Yosida, you know, that I'm talking about. So instead of just ring ideals, I'll work with ring ideals that also work well with order. So they're going to be ring ideals which are also convex, so they respect order. And now I want to take maximal such ideals, and then I want to define the topology, which in algebra is known as Zariski topology, which is basically generalization of how stone topology is defined. You just take an arbitrary L ideal and you look at all maximal ideals that contain it. These are the closed sets of your topology. And this famous result of Yosida in this language tells you that the space that you build this way is actually a compact Hausdorff space. And this is why these spaces are known as Yosida spaces. This is also sometimes known as the whole kernel topology. These are all the same, different names of the same thing. And then, so now we have this functor that associates with each bounded Archimedean L algebra, the compact Hausdorff space of maximal L ideals. And now we have two contravariant functors, and we want to understand how they act. So the first thing is that each algebra we can embed the same way that each Boolean algebra you can embed in the power set of its stone space. Each algebra, now each BAL we can embed into all continuous functions. Now, how are we going to do that? that also involves a couple of very famous theorems in mathematics. The first theorem is the so-called Hausdorff theorem that goes back to the beginning of the 20th century. And what it basically tells you is that every Archimedean L group, linearly ordered Archimedean L group, is embedded into the reals. And in particular, when you have the R action on it in our setting, it simply means that if you mod out by a maximal ideal, what you always get is the real numbers. This is exactly what was missing when I was talking about these Gelfand rings and Schiff representations, because these are the stocks. And these stocks could be different unless you add additional structure, order structure. And as soon as you add this additional order structure, then the stocks become exactly the real numbers, which is exactly what we want. And so now what you can do is that you can associate with each element A in our algebra, we can associate a unique real number in the following way: that take the coset of this set, take A plus X. This coset actually, because of Hölder's theorem, is determined uniquely by a unique real number. I'm calling it lambda, and this allows us to define a function, and this function will be functional representation. This will be the representative of my element A. And now this assignment will give me an embedding of my algebra into the algebra of all continuous functions. And now the question becomes, in general, this is not going to be an isomorphism. And now the question becomes, what does it take for this zeta to be an isomorphism? And now here comes the second famous theorem in mathematics, the Stone-Weierstrass theorem. And so what's happening is that the image, zeta image of A, separates points. And now Stone-Weierstrass theorem tells us that because we're over compact Hausdorff spaces, it tells us that we can separate. As soon as your subalgebra separates points, that means that this subalgebra becomes uniformly dense. And so if you start from a uniformly complete algebra, then a uniformly complete algebra being uniformly dense exactly means that we have an isomorphism. And thus we obtain this representation theorem that every BAL you can represent as a uniformly dense subalgebra, and this subalgebra becomes the entire C of X if you start from a uniformly complete element. So is the sun getting in the way?
No, it's okay.
Is it okay?
Yeah. Mm-hmm.
Okay, so now we're getting our junction and duality. So we have these two functors, and one of these and then these two functors come with their units. Since I have dual, usually you talk about units and co-units, but we have this dual adjunction. So it's hard to say which one is unit and which one is co-unit, because you turn things upside down and then whatever was unit becomes co-unit and the other way around. And so what's going on is that we really have this dual adjunction, one unit of which is exactly this zeta, which allows our representation. And on the topology side, we get this epsilon. And how do we define epsilon? This is exactly the same way as Stone duality works. You look at all the functions. In the Stone case, you would look at all the elements, all the clopens that contain this X. And that means, remember, clopens we're identifying with continuous characteristic functions. So these are exactly all the continuous characteristic functions that send this X to 1 or 0, depending whether you work with ideals or filters. And so when we work with maximal ideals, we want to look at all the functions that vanish at this point X, and this gives us exactly this maximal ideal that is uniquely determined by this point. And so here is this is Gelfan duality right here. So what I have on this slide is exactly this, what is known as Gelfan duality. So what we have is that we have this dual adjunction between these bounded Archimedean L algebras and compact Hausdorff spaces. And then when you restrict your dual, and here's another typo, this bottom BAL should be U BAL. So then when we restrict everything to uniformly complete objects, then this dual adjunction becomes dual equivalence. Right? So let me tell you some. So this is a more.
I'm sorry, there is a question.
Yes.
Maybe I missed something, but so you didn't say that there are any conditions on the norm of this Archimedean algebra.
Yeah, it's complete. It's complete.
And that's all. It's not there's no compatibility conditions with the algebraic structure.
It follows. It follows because the norm is entirely determined by the order. And so the next slide is going to explain some of what you're asking.
Okay. Okay.
But so there will be compatibility. So this is going to be what they call Banach algebra, you know. So we're
okay. My question is probably that it follows that it will be indeed a sort of C-star algebraic norm.
Yes, that's on the next slide. Just one more minute, okay? Okay, so here's the history, right? And so the C-star algebras will come up in a minute now, right? So the history, everything that I presented is real valued, but you can do everything working with complex valued functions. The reason that I didn't want to work with complex valued functions is that then the order disappears, because there's no good order on complex valued functions that works well with the algebra operations. So what I presented is basically the approach that originally Gelfand took in 1939, and then Stone did independently of him in 1940. There's another line of research which was done by Gelfand and his collaborator Naimark in 1943, where they actually worked with complex valued functions. So if you work with complex valued functions, you don't need your order at all. All you need is just the norm. And then what you get if you take this norm is exactly what's known as commutative C-star algebras. But the important thing is that it doesn't matter, in the commutative case, it doesn't matter whether you work with the C-star algebra structure or whether you work with what I call this Bell structure, because you can go back and forth. If you have all complex valued functions, that you can recognize real valued functions as self-adjoint elements. Those are, remember, when you're complex valued, there's always this adjoint operator, this star operator that you have, and then self-adjoint elements with respect to the star operator are exactly going to be your real valued functions. And if you have your real valued functions, how do you go to complex valued functions? All you have to do is to tensor your real valued functions by complex numbers, and then you get back to this standard, more functional theoretic way of doing things as commutative C-star algebras. So commutative C-star algebras and these uniformly complete Bells, these are two different sides of the same coin, right? So you just have one coin. On the one side, you just work with complex valued and norm, or on the other side, you can work with real valued and order, and the two categories are actually equivalent. What's missing from this history is the work of this Kakutani, and then Krein brothers, and then Yoshida. They actually worked with a different signature. They didn't take this ring multiplication at all. All they wanted to work with was this vector space structure. And so they worked with vector space structures, and then they only added an order. And so in fact, what happens when you work with this uniformly complete such objects, these are known as vector lattices or spaces in the literature. Then what happens is that this multiplication is recoverable, because basically what happens is that these objects will also become exactly C of x for some compact Hausdorff space x, and then multiplication becomes definable, because you can think of elements as just functions into R, and you can define multiplication that way. So this is the history behind these things. And now the question is that how is this, and in a way, calling this Gelfan duality, the same way calling Jonsson-Tarski duality is some kind of misnomer, because it was really other people who did it. Only calling this duality Gelfan duality is also misnomer, because there was also Naimark involved, there was also Stone involved. So in some of papers, you will see that this Gelfan duality is also referred to as Gelfan-Naimark-Stone duality. So now the question is, and this is actually how, now the question becomes, what are the connections between Jonsson-Tarski duality and Gelfand duality, right? Jonsson-Tarski duality takes stone duality and then tells us how to incorporate in stone duality operations on Boolean algebras. So a natural way now is to take Gelfand duality and talk about how to incorporate additional operations on these rings of continuous functions into the picture. So these continuous relations that I talked about, they have natural generalization to the compact Hausdorff setting. All you need to do is that remember that a relation was continuous on a stone space if inverse image of clopen was clopen, but you may not have clopens, right? So instead of working with clopens, you have to work separately with closed sets and open sets. And if you work separately with closed sets and open sets, then you need a condition on each one of them. You need to talk about R inverse of closed being closed, and you need to talk about R inverse of open being open. And in the setting of compact Hausdorff spaces, then again, we have the same connection between continuous relations on compact Hausdorff spaces and continuous functions into the Viatori space. So the entire theory generalizes to the setting. And in fact, the entire theory was done for compact Hausdorff spaces. And then simply modal logicians restricted this situation, this more general situation, to the setting of stone spaces, right? Because they only needed stone spaces for their considerations, right? So now the question is, how do we define box on the Boolean algebra of clopen sets of a stone space? This is the standard definition, right? So you look at all the points whose R image is entirely in the set, and you say, this is how I'm going to say. I'll say that X belongs to box if and only if the entire R image of X is inside U, right? Now, of course, what I want to do, I want to define box on continuous functions now, right? And so instead of working with subsets, I need to work with the corresponding characteristic functions. And one observation is that the characteristic function of box R of U is simply going to be the infimum of the characteristic function of the R image of X. And that allows us to define a box on continuous functions. All you have to do is to look at what points X is, then take its image into R, and then take the infimum. Now, the infimum is possible provided Rx is non-empty. If Rx is empty, then because R doesn't have bounds, then you cannot define infimum if R of X is empty, and hence F R of X is empty. And in that case, we simply manually define. We kind of think of R as being 0-1 interval. And if you're 0-1 interval and you take the infimum of the empty set, then it's 1. And so we manually define box in that case to be 1. And this is exactly the part that makes some of the calculations unpleasant. So all the demonstrations I'll do will be for the case where R of X, where the relation is so to speak serial, meaning that R of X is always non-empty. Right? So now here's a proof sketch. I'll do it very quickly of why this box R is well defined and why it produces a continuous function. Well, compactness is essential here, right? Because R of X is closed, so it's compact. So then we can achieve the infimum will be attained on this set, and it's simply infimum is going to become minimum. And so then we're well defined. And then continuity follows from this observation that box R F inverse can be calculated. Box R inverse of lambda infinity can be calculated as the complement of R inverse of the complement. And observe that I'm using all this. Look at these three properties of Rx. Where are they? These three properties that R image is closed, R inverse of closed is closed, and R inverse of open is open. I'm using all three here in this little proof because I'm using that R image of X is closed to say that infimum is attained. And I'm using in this first equality, I'm using that R inverse of closed is closed because F is continuous. So F inverse of this open set is open. So its complement is closed. And here I'm using that, right here, I'm using that R inverse of this closed set is closed. That's condition 2. And down here in the last condition, F inverse of minus infinity lambda is open. So F inverse of open is open. And right here, I'm using that R inverse of an open set is open. So I'm using all three conditions here to conclude that box R is indeed well defined. And then you can also define diamond. You just dualize things. Instead of working with infimum, you're going to work with supremum, provided Rx is non-empty. But if it happens to be empty, then we just say that then diamond at X is simply 0 here. And like in Boolean case, we have that diamond and box are interdefinable. And in the good case, when we have a serial relation, then box is simply infimum. That's very similar to what happens in the Boolean case. It's also infimum there, but only infimum when you work with characteristic functions. Diamond is supremum. And here in the serial case, this correspondence between box and diamond is exactly like in Boolean case. Here's a picture that shows you what we really are doing. If it so happens that your relation is a partial order, then take your function f. Blue is this box. What you're doing is that you're taking the greatest order preserving function underneath. And the red one is your diamond. That's the least order reversing function or decreasing function above your original function. And so when you're doing these type of calculations, drawing these functions and then doing these calculations, doing this little bit of geometry of how these functions look like is very convenient. So let me quickly go through these properties here. These are the properties that, that this box satisfies. And this is actually the axiomatization of box in this setting for this C of X. That look at the axiom 1. This is standard. You have the same axiom for Boolean algebras. Axiom 2, what you have in Boolean algebras is that instead of lambda, you have 1. But now instead of just 1, we have actually all possible values. Lambda can be any real number, and box will preserve it. And observe that I'm making this assumption that R is serial here, because when R is not serial, then box R of 0 is not necessarily 0, and this axiomatization becomes a little bit uglier. Axiom 3 simply tells you that box preserves the positive form. Axiom 4 tells you that if you translate, box preserves translation by a scalar, that if you apply box to a translation, that's the same as to first apply box and then translate. And axiom 5 basically tells you that if you multiply by a scalar, box respects multiplication by positive scalars. You can apply box to multiplication by positive scalar. That's going to be the same as first to apply box and then multiply by positive scalar. Things become uglier when we go to the general case, because now you have to carry box R0 with you, because this is no longer 0. And so the axiomatization becomes a little bit uglier, but I won't spend too much time on that. This is the main category, right? So this is the category. So now this is an axiomatization of this box operator on any of these unbounded Archimedean L algebras. And observe that again, I'm carrying this box 0 around. If box 0 is 0, then this axiomatization simplifies. And so the same way that these Boolean algebras with operators generalize Boolean algebras, these modal balls generalize. These are basically these Gelfand rings with this additional box modality on them. Right? And so now you can go back. So I'll go very fast now, because otherwise I will never go through this. You can go back now by taking Yosida space, and the same way that we define relation in the Jonsson-Tarski duality, we're doing the same thing here. It's basically the same relation R as you define in the Jonsson-Tarski duality. It also makes sense from ring theoretic point of view, because what's going on is that X's are related to Y if and only if for each positive function, whenever the function vanishes at Y, then box of it should vanish at X. And so it also makes sense from ring theoretic point of view. And this is the main technical difficulty that we faced when we were doing these things, that you need to prove that so defined R is actually a continuous relation. So this actually required a lot of machinery from algebra, but also from modal logic. In particular, there's this famous Esaki lemma that makes this Jonsson-Tarski duality works smoothly. And then we also needed this Sasaki lemma here. I'm skipping all these details here, but this was the main technical challenge for obtaining this duality. And so now what I have is that we have this generalization of descriptive frames, right? Descriptive frames are stone spaces with continuous relations. What we have now is, instead of stone spaces, we have compact Hausdorff spaces with continuous relations. And so I call this Vietoris frame because I don't have a better name for it. But somehow this is related to this Vietoris construction. So this Vietoris frames generalize these descriptive frames. And now what we have this category of Vietoris frames, and then we have this functor C that associates with each compact Hausdorff space, the ring of continuous functions generalizes here. Now all you need to do is just to define this box through the infima the way I defined. And when you go back again, you take the Vietoris, the Yosida space, and then you have to define this R relation on it. And then the end result of this is the generalization of Gelfan duality to the setting of compact Hausdorff space, to the setting of modal operators. So again, what's going on here is that we have this dual adjunction between modal bells and Vietoris frames, and this dual adjunction becomes dual equivalence when you restrict to the uniformly complete objects. And there's another way to obtain this duality as a direct duality of corresponding functors, the same way I talked about how you can obtain Jonsson-Tarski duality by lifting up stone duality to duality of the corresponding functors. So on the topology side, you would have Vietoris functor, but on the algebra side, you will have to define a functor which generalizes this free functor that I was talking about in the Jonsson-Tarski case. And there are some technical difficulties to overcome here also, because we need to develop the machinery of free algebras in BAL. And remember that unlike Boolean algebras, which is a variety, which is closed under homomorphic images, subalgebras, and products, some axioms of BAL are not equational, like its boundedness and Archimedean. These are not equational properties. And so free objects don't exist in BAL in their standard form. And in fact, you have to adjust things very carefully. But again, I'm skipping the details because I'm running out of time. Let me quickly talk about some consequences. So first of all, you recover stone duality from Gelfand duality in the following way, that up here, what I have is this U-BAL is dual equivalent to compact Hausdorff. That's Gelfand duality. And down here, the stone and Boolean algebras, I have this dual equivalence. This is stone duality, right? So what you can do is that instead of Boolean algebras, what you can work with is you can work with the so-called clean U-BALs. These are exactly, a ring is clean when it has a lot of idempotents. Idempotents exactly correspond to clopens on your dual side. And so you need to have a lot of clopens. You need to have a basis of clopens in order for stone duality to work. And so this is exactly the ring theoretic condition that guarantees that. And then what I have here, this duality between CU-BAL and stone, that actually can take the role of stone duality. And then you can recover the stone duality by taking this idempotent functor that will associate with each BAL its Boolean algebra of idempotence. So that's how you get stone duality from here, right? Now, in a similar fashion, you can get the Jonsson-Tarski duality, right? Because now you take the previous picture and you add modal BALs everywhere. So instead of U-BAL, here you get modal U-BAL, and instead of CU-BAL, here you get modal CU-BAL. And then here, instead of compact Hausdorff, you get Vietoris frames. And here, instead of stone, you get descriptive frames. And then these modal algebras you can recover as idempotents of the modal clean U-BALs. And so Jonsson-Tarski follows. Here are some correspondence results that I wanted to mention, that you can develop correspondence theory in modal logic. What it does is that it tells you how you can axiomatize some properties of relations, continuous relations, by means of the correspondence axioms of modal logic, or the other way, you can have some axioms of modal logic that have very nice first order correspondence on the semantic side. We can do the same thing and observe that this second slide is exactly under the condition of seriality, then this reflexivity, transitivity, and symmetry are characterized exactly the same way as in modal logic. Not in general, because you have to carry this box 0 along, but as long as box 0 becomes 0, then this disappears, this disappears, this disappears, this disappears, and then your axioms become exactly the same as in modal logic. Right? Now, there's this famous theory of canonical extensions that, that Jonsson and Tarski developed. So this is one of the active topics of research in modal logic, right? And so the way that you can realize this canonical extent, so you can define them purely algebraically as those complete and atomic Boolean algebras that satisfy this additional density and compactness conditions. But then you can realize them as the power set of the stone space of your Boolean algebra. And we can do the same in this more general setting, but remember that clopens get replaced by continuous functions. Now, how should we replace all subsets? Remember that clopens were continuous characteristic functions. So now you can work with all characteristic functions of all subsets, and then you can generalize that, and then these generalizes to all possible bounded functions. So what I'm doing is that I'm dropping continuity now, but I'm still retaining boundedness, that the image has to be bounded by some numbers, right? Some minus n and plus n, right? And then you can develop this theory of canonical extensions in this more general setting. And those of there's this famous Salquist theory in modal logic, and my sense is that that can be developed also in this more general setting. And this is something that is not done yet. Finally, compact Hausdorff spaces admit other dualities. There are some dualities in point-free topology and domain theory that play an important role. So there's the so-called Isbell duality, when you, instead of continuous functions on compact Hausdorff spaces, you work with all open sets, and then that gives rise to the so-called Isbell duality, which plays an important role in point-free topology. And there's also this De Vries duality, which in the De Vries case, instead of working with all open sets, you work with regular open sets. And obviously, there's connections between Gelfan duality, Isbell duality, and De Vries duality. And this is something that that you can work out the details, but I'll save you from the details here. I guess I'll just stop here. So I hope that these gave you some idea about how these ideas from the branch of mathematics that allows you to present Gelfand duality, how you can use these ideas to generalize this theory or this Jonsson-Tarski duality to this more general setting of compact Hausdorff spaces. I'm happy to take whatever questions you have.
Okay, thank you. That was certainly a lot to think about. I mean, this whole
yes, this whole direction.
Going generalization.
I'm sorry that I threw a lot of things at you, you know, so I
Mhm.
apologize for that. But
yeah, you don't have to.
There are beautiful things, Guram.
Yeah.
thank you.
For a mathematician, very smooth and continuous, yes.
Okay, who has any questions? If not, I will ask a very general kind of
Yes,
question. So the main idea that you wanted to convey, I think you conveyed very good. I mean, we see that this whole business that model logicians have been doing for Boolean algebras for a long time can be carried out to this more general context, and it relates to all these interesting structures studied by topologists and functional analysts.
Yeah, so-called real mathematics, yes.
real or complex.
Or you can do complex. You can do complex too. Yes.
Okay.
Mainstream math.
That was the main message. Yes.
But of course, we would like to see some, I would say, concrete examples for concrete spaces. So I suppose that in mathematics, this dualities and algebras appeared not for nothing, and there are concrete examples, concrete operators on these algebras that are of interest for some reason. Does your theory say anything about, let's say, are there such examples that you know of and can demonstrate?
Yeah, there are many examples, right? So, for example, there are some very difficult open problems in ordered algebra. There's a think about just 0, 1, and now look at all continuous functions from 0, 1 to R. That's a well-studied object. Of these functions, there are very special ones, the so-called polynomial functions, right? Now, what you do is that polynomial functions don't form BAL yet. So what you need to work with something bigger, the so-called piecewise polynomial functions. So basically what you do is that you break your 0, 1 interval into several pieces, finitely many pieces. And then on each one of them, you just draw some kind of polynomial, say x squared or something like that, but then you connect them smoothly. So it's it still stays continuous. So these are the so-called piecewise polynomial functions, right? So these are examples. Remember that main motivation was C of x, but remember C of x, these are uniformly complete objects, but this category BAL is bigger. And there are objects that are not of C of x type, which are more hands-on objects. C of x is too big, so to speak, but these polynomial functions and piecewise polynomial functions, they are smaller. You can work with them, right? And so there are lots of open questions from algebraic geometry about how these piecewise polynomial functions behave. And so there's this famous Peirce-Birkhoff conjecture, how to describe free algebras in these BALs, right? That are these free algebras on finitely many generators, exactly the piecewise polynomial functions. And so all this direction about piecewise polynomial functions relates to this hands-on activity that people in algebraic geometry do. But some of these are difficult questions to solve. So the Peirce-Birkhoff conjecture, it's open since 1956. And so what we can prove here is that these piecewise polynomial functions, the free algebra is embedded in piecewise polynomial functions, but whether or not it coincides, I mean, that would solve a major problem in mathematics.
Okay.
There are other examples too. This is just one example that I gave.
Okay. Daniel wants to ask a question.
Oh, yes, thanks. I have a question about Sahlqvist and perhaps an idea. Does it make sense to develop Sahlqvist's theory for these algebras, perhaps generalizing some techniques from the paper by Jonsson called On the Canonicity of Sahlqvist Identities? I can send.
No, I have the paper. Yeah, I'm familiar with this is like from the 90s, right? Like 91 or 89 or so, some late 80s, early 90s, right?
Yes.
Yeah. So
94.
Huh?
94.
94. Right. Yeah. So since then there have been some other directions. There's this entire May-Gerke direction, what I call May-Gerke direction, of recognizing they actually generalize Boolean algebras to the setting of lattices and then even posets, and that they developed some interesting techniques to study exactly which identities are canonical and develop different versions of Sahlqvist theory. And so So I think that some of these techniques, including Jonsson's technique, will apply, but the extent to which they will apply, I don't know yet.
Okay, thanks.
Mm-hmm.
Okay. Other questions? What will happen if you, Guram, if you try to, let's say, relax the condition on the reals or that you have, and so you consider a function not in, let's say, complete Archimedean ordered field, but into something more general.
Yeah, so there are several. These type of relaxation can work both ways. So you can relax some properties on R and actually work with arbitrary ordered fields, and then on the other hand, on the topology side, you can also relax things, right? Because you can relax the compactness condition and work with, say, Tikhonov spaces or completely regular spaces, right? And so both of these directions have been studied. And so in particular, you know, if you relax things on the topology side, then instead of working with entire, so what happens in compact case is that C of x is the same as every function from C of x is bounded. So if you relax that and you work with an arbitrary Tikhonov space, then C of x is bigger than the bounded part of it. And so you have to play a careful game between C of x and C star of x, right? And these are two different rings. One is C star of x is a subring of C of x, but it doesn't coincide anymore. It's only the compact case that allows these two things to coincide. So there's entire theory in that direction, because now the boundedness axiom goes away. You don't have boundedness axiom anymore, right? And so there has been a lot of topologists and mathematicians struggled to find a nice axiomatization of this C of x's when x is not compact. And there's this entire theory that the so-called Hewitt real compactifications and things like that are relevant here, right? So I think that it still remains an open problem to obtain a nice duality for C of x where x is completely regular. And there are some recent attempts involving some of my team members in how to resolve this issue. So that's the topological side direction. What you asked is what happens on the algebra side direction, right? And so as soon as you drop Archimedean, that what you get is a very different world, you know, because Archimedean is very different. So already among linearly ordered algebras, there will be these algebras that have infinitesimals, right? And so I think that you can develop some of this theory there also, but I don't have up to date knowledge of what exactly was done in that direction. But I think that this was considered, you know, so non-Archimedean algebra is a big branch of algebra.
I have a question.
Please ask, yes.
Well, it's probably it leads to nothing, but it is somewhat natural. So like Gelfand and construction generalizes not to a duality, but to something that you can do with non-commutative operator algebras. So do you think, or maybe, I don't know, is there anything interesting like in this direction?
Very good question. You can almost win a Fields Medal, you know, if you do that. That's a very good question. Yeah, these operator algebras, difficult outside of commutative case. There are some very, very difficult theorems, right? That
how do they relate to what you have told us?
well, they are more general, right? I mean, we have commutative case, so ours is a very, it's a subfield, right? So we are only looking at commutative C-star algebras, and now drop commutativity, right? So you're talking about operators on Hilbert spaces, and you no longer have commutativity, right? So then, how to represent these objects? I mean, that's there are some very deep theorems in this direction, right? But this Gleason's theorem being one of the highlights, right? But I don't see, I mean, our approach is very commutative algebra approach, right? So outside of commutative, this will not work the same way in the non-commutative case. Nevertheless, this is a very good question, because I wonder what can be, if something can be done in that direction. So this approach, I mean, quick answer is that this approach will not directly generalize that. And then whether there's a possibility to study these objects using some of this technique is a very, very, what is the word I'm looking for? Intriguing direction for me. I didn't answer it well, but this is the best I can do.
I didn't expect. Well, answer is expected.
Okay. Valentin Borisovich, you must have many questions, but you keep silent.
I keep silent. It's fantastic. Yes, I can. I can only say that it's fantastic. Yes.
We're still working on your previous question from 6 months ago, you know.
Yes.
Then don't ask any further questions.
I won't. No.
We're still working on it. We're getting close to it.
You're working on my questions too.
No. I asked something at another talk. Yes.
Yeah, we have your questions also in the back of our mind, Val.
Sorry?
We have your questions also in the back of our mind.
Aha, so they are waiting there in the queue. Yes.
They are in the queue.
It was just to say it was a wonderful talk. I wish I was more fresh to be able to follow it in real time, but I had 3 hours of lectures before that, so I couldn't follow that much. But I would like to be able to see the slides if they are available.
Yeah, I'll fix this couple of typos that that are there, and then I'll email them to Lev.
Yes, we will put them next to the video of your talk. So there is this matnet.ru page where the videos are posted, and then all the materials are also there, including abstract and slides.
Yeah.
Okay, Guram, thank you very much. That was indeed quite an
Thank you
interesting
for listening,
field.
and thank you for your patience.
Yeah, I still remember that you had 5 topics at some point, and you just covered 2 of them. Somewhere in the spring, we would like to hear the 3rd one. That's
Okay.
what I wanted to say. Okay, good. Yeah.
I'll stop sharing the screen, right?
You can, yes. So let me just make the announcement that next Monday there will be talk by Tadeusz Litak at this seminar, and tomorrow there will be this seminar on algorithmic problems in algebra in logic, where we will have a talk on group theoretic analogues of post-correspondence problem by, I forgot the name of that, but anyway, tomorrow there will be some interesting, I would say, talk in combinatorial group theory. Okay. Thank you very much.
Thank you.